Well, on the inside, T infinity on the inside is just going to be 70 degrees F. T infinity on the outside is going to be adiabatic wall temperature, and that's going to be example.
Yeah, it's colder on the outside.
Example 511 in Holman.
It's hard because you're gonna
Example
have that
511
heat
shows you how to
built
get this.
up.
And even though we actually have an actual T
But you
infinity
still
up
got a
here,
70-degree.
we can't use this. We have to use this value right here. Essentially becomes our new T infinity close to the aircraft.
And you said last night that T infinity
No,
right there is like an
the
ambient for
outside's
that,
what we
on the Excel sheets.
Yeah.
And you have to use that, like, I saw like an equation with like R equals like.
Like the saturation.
T A dot wall minus T infinity over T naught minus T infinity, right? That's exactly what you use.
Is that T naught, like, what's the difference between that T naught and T infinity?
Okay, T naught is equal to T infinity times 1 plus gamma minus 1 over 2 Mach number squared. Gamma
Gamma's 1.4 for.
Gamma's 1.4.
Okay, I was playing with that last night. I had no idea what gamma was. How should we have
And then
known
you
that?
take the
It's just
T-naught,
for, the gamma for air is
It's for air.
So
Yeah,
just use
I mean,
Okay.
this was, we,
Oversight.
yeah,
and
so,
then, sure, and then you take the T naught, and they had that equation Prandtl raised to the 1/3 or R. equals-
yeah, so then,
Yeah,
so then there's another recovery factor out here, where your recovery factor is T adiabatic wall
Yeah.
minus T infinity over T naught minus T infinity. And this recovery factor is actually just Prandtled to 1/2. That's why, like, whenever I talk about this in loose terms, I say that your adiabatic wall is going to be about 80% of the total temperature rise between free stream and total stagnation, right? Because the square root of 0.7 is going to be like 0.8, right? Square root of a fraction is going to be larger than the initial fraction. So 80% is equal to this delta T over this total delta T.
So, 2 questions real
What do we
quick.
know?
Isn't there 1/2 for laminar flow only, and then 1/3 for turbulent?
This is laminar, right?
If it's turbulent, I'm sorry, then it could be 1/3.
And then the second question
Well,
is this laminar
Yeah,
or
it's
turbulent?
No, it's
one-third.
It's 1/3, so.
1/3. It's 1/3.
Definitely heard of it.
yeah, we're definitely turbulent here, so let me,
It's the 1/4.
I think I have pieces to these get started.
Sure, what temperature will dew point be affecting? Is that gonna be your wall or your inside of your cockpit?
So all I need.
I'm sorry, for turbulent flow, it's 1/3. What's the cube root of 0.7? We all have phones, I don't.
Not on me.
You root of 0.7.
Cube root of 0.7.
Why are you using 0.7?
That's the Prandtl number. Prandtl number for air is roughly 0.7 at most temperatures.
So what about the Prandtl number that you could calculate from the tables that you gave us?
It's going to be really close to 0.7. You can either look it up as a function of temperature, or
Plug in 0.7 by hand for every single one.
I do 0.7 by hand. I do 0.7 in my mind because I don't have my computer in front of me.
Yeah, that's what I'm saying.
0.7 is
we
usually
could
pretty
use
good.
0.7. We don't have to use any of the PRs.
I would prefer you use, if you got the computer there, I'd prefer you use the more precise Prandtl number rather than
The
I'm standing
interpolated
in
one?
front of a classroom 0.7.
Sure.
What's it?
I was just saying for the you can interpolate that one.
Well,
What's the?
well, no, what's 0.7 raised to the 0.333 power?
On that test.
What's the cube root of 0.7?
And so,
0.88.
0.88, okay.
for the dew point temperature, I know we're gonna have to calculate from the outside. Do you also want us to calculate the dew point temperature for the inside?
Yeah, how's
Oh, yeah.
How's
So
the
for
dew
both
point?
sides then?
Yeah, you gotta do it on both sides.
Okay.
So on the inside,
I thought you said to assume that
65 or something.
the outside was at saturation already.
right, so if the outside's at saturation, here's the, okay, so here's, because this is a flight idle descent,
Sure, I don't understand how dew point's gonna be. What is it gonna be affecting at the temperature? Like, how,
Yeah.
is it both temperatures are gonna be changed? Like the cabin and the outside wall?
the absolute humidity on the inside of your cockpit is going to be whatever the absolute humidity is on the outside. However many grains per pound of humidity, grains per pound of water per pound of dry air you have on the outside, That's what's, absolute humidity is gonna be the same on the outside as the inside. It's a flight idle descent, that's a very good approximation. Because your engines aren't at enough power to properly run the ECS system during the descent. So if this is the case, you wanna calculate, once again, on the inside, do your relative humidity for your vapor pressure versus PSAT. And you want to make sure that this is less than 1. And, all right, so your PV, all right, your PV comes from this, okay? Your PV comes from this. This P is your cabin pressure, and it follows your pressure schedule during the descent. During your descent, is there any way we can turn that light off? You guys probably can't see because of the glare.
It keeps turning back on.
Yeah, that's really weird.
Nothing mind.
There we go. So, I think every time I bump the stand, it turns back on. So, inside, so our absolute humidity is going to go from outside to inside. It's going to go unchanged. But the difference is inside, we're going to calculate, so we know what W is. We know what this is going to be.
Yep.
Let me write it. Okay, so we want to solve for PV.
And then you plug that into your phi equation.
Yep.
And then
And just verify that you're always below 1 when
interpolate.
evaluated at your wall temperature.
Either do that, or you could interpolate. You could find P saturation based on that, off of that, and then interpolate dew point temperature if you set P equal to 1, right?
Is
And
cabin-
that would actually give you the temperature of dew point, wouldn't it?
Does cabin pressure schedule change?
Yeah, you could do dew point temperature. You could plot dew point temperature, and that would be
Should we do phi, or should we do it based on phi or based on temperature?
either one, as long as you give me a plot. So you could plot dew point temperature. You could plot phi on a secondary axis, or you could plot, T dew point. You could plot like the dew point of the cabin,
Okay.
or you could plot on a secondary axis your relative humidity
Yeah.
as a function of time. So you need to show me that you need to show me that, and this right here, this area under the curve right here, right? This negative area under the curve. This is what we want to avoid with our.
Yeah.
This is why we want to.
And we only have to do this on the inside, right? Because the outside's not going to fall in the car.
No, that's not true, because in this region, this could ice up. This could ice up at higher altitude. It could fog up at lower altitude.
Okay.
So, this negative region is why we want
You just do the same process, though.
same process, same general. So this white foggy area.
Yeah.
Is it the atmosphere or the?
Inside the cabin is the actual.
So with window heating, we'll keep our temperature above the frost point or dew point with window heating. That's for the exterior, and
Say watts over Q dot?
with
Okay.
Q dot.
Is it okay to put Q in multiple places in the window, or just one?
I would just put it in the center strip.
Alright.
I would just put it in the center strip. That way it's most effective. It can help
But the convection coefficient's way higher on one side, so wouldn't you put it to one side if it's off by?
Wait, why is it way higher on one side?
Because it's moving on the outside. So you have like 100 here, you have like 2 here. So you would think that you'd want
To
to
move it to
Oh,
the
yeah.
inside.
to the inside. But then then you got more thermal lag to get to, so it's putting it in the center. I mean, you can put it wherever you want. That's a design decision for you. I would just put it in the center, but you can, yeah, you might have a solution where it works, where you can use less wattage to accomplish the same thing by moving it closer to the inside. And this here is with,
And what kind of convection coefficients are you thinking? I mean, between 100 and 200 for the outside. Is what you
yeah, like roughly
Inside.
100 on the outside. On the inside,
got like
1 to 4, 1 to 8 maybe. I mean, not much.
what if it's like point something?
Yeah, it could easily be like 0.5.
I mean, it goes from,
could be
like,
very, very
About
low.
point.
It goes from 1 all the way down to 8.
5 to 9.
Is that what you mean by that?
I mean, it just depends on. It all depends on where you are on temperature. I mean, there's no one answer. It's all a function of what your temperature distribution is. So yeah, it could be half. If it's significantly less than a half, like if it's an order of magnitude less than a half, I'd be a little bit concerned.
So is the H different from metric to English?
Yeah.
So
Yeah, you can't, you're in like BTUs per hour per square foot
Okay.
versus watts per meter.
Sorry, one last quick question. With that cabin pressure, I'm really confused, like how to get that.
The cabin pressure?
That's right.
Well, I gave you a pressure schedule. So you got,
like 8,000 feet, 5,000 feet.
at some outside altitude, you're gonna be at some. There's a table in the Excel file where,
Okay.
So just copy and paste that into the sheet, or use the linear interpreter.
Yeah, I do know about it.
Can we interpolate that table? Because technically it's not an interpolated value for that.
oh, for this table?
Yeah.
Yeah, interpolate it.
Oh.
Yeah, that's exactly what the software would do on the aircraft to
Oh.
maintain that pressure. I don't know. Yeah, it's whatever the schedule is. Okay, course evaluations. I was supposed to give you 10 minutes at the end of class to do course
We're gonna
evaluations.
do them anyways.
You weren't going to do them anyways?
Nobody does their course evaluations in class.
Okay, so just
I did.
remember to get your course evaluations in. I think that this is probably a more useful part of time.
Yes.
Yes, sir.
Is that 10.8 again, sir? 41,000?
Well, I don't remember what it is,
Do you
but
use-
this is,
do you
whatever I type
metric
in there
or
is what you
SI?
want to use.
Yeah.
I use
Those are
metric
just,
stuff.
you
I
know,
was not
some
gonna
dummy
do that in
values.
English.
Sir, thank you for the help.
And
You
use
all
your,
in like meters
the
and
linear
Celsius.
interpolation function will, even though,
Then I've gotta go
even though this
convert
is
all
like,
these
even though
tables.
this,
So what?
Well, this one's gonna be, it's in
Even
PSI
though this is like a
and
step-
Fahrenheit.
a
I've
step
gotta put it in
function.
Kelvin and.
the linear interpolation will.
So you think it's
I
easier
put
to do it
I put it
in
for the
SI?
steps.
That's how I did it. You have to convert
steps are
stuff
correct.
initially
The
when you
steps
do
are
that,
correct.
but you
We
don't
have
have to worry about
it'll-
all the
it'll
weird
work
conversions with BTUs and shit.
So what equation do we use?
Yeah, G sub C is one.
I'm trying to do that.
T-ball on the inside.
Whenever we get to
Well, the